Well, we've talked about Newton's three laws of motion, and we've done some problems, and we even introduced free body diagrams in the previous video. Let's take a second look at a free body diagram and do an example that involves a system of masses instead of just a single mass, and you'll see how free body diagrams make things easier. Let's try a problem like this. Now, let me describe what's going on here. This mass right here is hanging from a string around a pulley. We'll say for purposes here that it's a frictionless pulley, and it's attached to this mass up here on top of a horizontal table that's also frictionless. So if the table's frictionless and we attach a mass and then we let go, what's got to happen? If we cut the string, imagine for example cutting the string right there, this mass right here is going to fall at 9.8 meters per second squared acceleration, and this mass over here is just going to sit there. On the other hand, when we attach the string, if there's a whole lot of friction, maybe nothing will go anywhere and it'll have an acceleration of 0. But with this surface right here being frictionless, what has to happen is this must fall, because this will not offer resistance in the form of friction. But at the same time, the tension in the string pulling up on the mass means that it can't fall at 9.8 meters per second squared. So it's going to fall at somewhere less than 9.8 meters per second squared. And at the same time, this mass is going to be pulled horizontally at something less than 9.8 meters per second squared. Make sense? All right, let's look at it in a little bit more detail. Let's suppose we have a 4 kilogram mass on a horizontal frictionless table attached to a non-stretching string. Now, you can't have the string stretch, because if it does, it could be like silly putty and stretch until the hanging mass goes all the way to the floor without moving the one on the table at all. The string runs over a light pulley and is attached to a 1.5 kilogram mass. Find the tension on the string and the acceleration of the masses. So we're going to find two things. Tension, by the way, is a name for a pulling force. So let's sketch this again. Okay, here's our system of masses with our light pulley, frictionless pulley, and a very taut and very light string. If we call the top mass mass A and the hanging mass mass B, what we can do is we can draw a free body diagram for each one of them, because Newton's second law of motion, F equals ma, can apply to each one separately, and then we can put our results together to come up with our solutions. Let me show you what I mean. Let's have the picture again. And let's remember some information here. If we draw the free body diagram for mass A, here's what we need to do. First, we need to choose a positive direction. And of course, we have to list its mass. Well, the mass is 4 kilograms. That's an obvious choice for a positive direction, don't you think? And now on a free body diagram, we have to add to that any forces that are on it. Well, we know that one force acting on it is a force of the string pulling right. I called that tension in the original problem, so that's what we'll call it. There's no frictional force pointing backwards. Now there are two other forces. The weight is pulling down, and the normal force is pulling up or pushing up. But they cancel each other out because it's not accelerating either up or down. So we don't really have to worry too much about those two forces. There's our complete free body diagram. Now we're going to do a free body diagram of the other mass. There's mass B, and we show the same things. Now I want you to think about this. What would be an appropriate positive direction for B? Would it still be to the right? Of course not. How about up? Well, that makes more sense. But if we look at the positive direction we chose for A to the right, when mass A moves to the right, which way does mass B move? Yeah, it moves that way. So once we've chosen this as the positive direction for A, we have to choose down as the positive direction for B. Got that? By the way, if we had chosen left as the positive direction for A and up as the positive direction for B, this would still work. We list its mass as well. Now let's draw forces on this free body diagram. Well, one thing we know for sure is that it's the weight that's pulling mass B down. We'll call that m sub B times g. That's how you calculate weight, where g is 9.80 meters per second squared. So that's 1.5 times 9.8. And if you multiply that out, you get 14 0.7 newtons. Is that the only mass on B? You caught me. No, of course it's not. If that were the only force, it would be falling. So there has to be another one. And that other force is the tension in the string pulling up. Now the interesting thing is the tension in the string pulling up on mass B and the tension in the string pulling to the right on mass A are the same tension. Why? Because the pulley is massless and frictionless. It's an ideal pulley. And because of that, we have the same amount of tension in both parts of the string. So now what do? Well, Newton's second law says that the sum of the forces is equal to mass times acceleration. And we're going to do that for each diagram. For example, for mass A, these two forces cancel out. So the only force is the tension. And that's equal to the mass, 4, times the acceleration, A. That's it? Yeah, that's it. The problem is, of course, there are two unknowns in this equation. How do we deal with that? By looking at the other free body diagram. That's going to give us a second equation with the same two unknowns. Let me show you what I mean. With down as the positive direction, the weight is positive and the tension is negative. And so we're going to get 14.7 minus t, technically plus negative t, is equal to mass times acceleration. But wait a second, the mass is 1.5 kilograms, and then times the acceleration. Sum of the forces, positive force plus negative force, equals mass times acceleration. Newton's second law. Now we have two equations in two unknowns, and they're the same two unknowns. You can use whatever method you know from algebra class to solve this system and find the tension in the string and the acceleration of the system. My personal favorite is to just add the two equations because I see positive t and negative t are going to cancel out. So we get 14.7 equals 4a plus 1.5a is 5.5a. Well, that's really easy to solve. A little bit of quick calculator work and you'll find that the acceleration is 2.673 with some more information out here. If we round that to the correct number of significant figures, well, in this problem we only have two significant figures. We would round that to 2.7 meters per second squared. Notice something really important. It's less than 9.8, but more than 0, which is precisely what we expected. Okay, now that's only part of our answer. We also need to find the tension. How are we going to do that? Well, if you take the 2.7 and plug it back up into either one of these equations in place of A, you should be able to get the right answer. I'm going to take the first equation because, frankly, it looks easier. And so I write t equals 4 times, and I'm going to go back to the unrounded answer because I don't want to have an accumulation of errors. So we'll go back to 2.673. And when we multiply that, we get 10.69. What unit would that be? Tension, that's a pulling force. It's going to be in newtons. But we need to round it to two significant figures. We don't want to mislead anyone into thinking that we actually know the answer out to that level of precision. And so with two significant figures, we round it to 11 newtons, and that's our other answer. And we've worked a system of masses by using, well, a system of equations. Pretty sweet, huh? Now, it's possible that you've been shown a different way of doing this. If we consider the whole thing, and I'm going to put this off down here in the bottom. If we consider the whole thing as just one system, having a total mass of 5.5 kilograms with just one force on it, and that would be the weight pulling right here, we ignore all the internal forces when it's a complete system. The only external force is the weight. Okay? Then we would have that weight, which is 14.7, is equal to the total mass, 5.5, times the acceleration, a. That's still Newton's second law. External force equals mass times acceleration. Hey, that's this equation. Sure enough, we're going to get the same answer for acceleration. Problem is, we can't figure out the tension. We still need one of these two free body diagrams to come up with the tension, don't we? So free body diagrams, learning about them is essential if you're going to be able to do good physics. Now, hopefully this hasn't been too confusing for you, but I think you can see that we could have lots and lots of different systems free body diagrams would allow us to solve. This is just one example. Talk to you later. Bye-bye.